Hi, welcome to another video on my Arduino Mega2560 combined with pulse width modulation. Last time I tried to figure out why certain frequencies didn't match up with the code, and I primarily kept busy with this part. In the recent past it became very clear that the physiotechnic motors I'm using can be used from 30 Hz on. Using the prescaler, that's not a very big problem. However, when it comes to timer 0, which controls pins 4 and 13, there's a remarkable difference. They should be given the same output, and as explained earlier, this is an eraser, so it blanks the output. You assign the eraser to timer 0, and then with prescaler 5, which deals with a frequency of 30 Hz, you actually assign that frequency to, or prescaler, and thus frequency to timer 0, so you get 30 Hz on these two pins. As shown, the 30 Hz is assigned to pin 4, easily to measure, but not so for 13. And that is quite odd. Not that everything is the same, and not that everything is working fine furthermore, because for some reason a few things don't work out yet. But it is odd that these frequencies, that the frequency on these two pins are not the same. So for now I'm focusing on that, and that is let's say done in two ways. First, is this alright? And second, can I use some electronics to actually find out how and why? With that, I have still some space on the breadboard to see if everything works fine, so I can put a resistor and an LED and see how that works out. They should be acting the same then, but as the frequency measurement on 13 shows out, they most likely won't. So a wire is present, a resistor is present, I have to prepare an LED, and then I have to find this information to confirm whatever I've done. So first of all, hardware setup. So provided that this LED actually works, let's put it just here on the breadboard. Then one of the many resistors. And I have to be careful to put that in a way that it won't interfere with these resistors, but it's now in a lane that is safe. Then this wire anywhere in this lane, and keep in mind that this is a lane that it's not connected in that direction. Well, with that said, I can actually start measuring something. "20 kilohertz, and something is not working here, but let's see if that is the only problem. So probe on the minus and a probe here, and a probe here, shows it's 12 kilohertz, while a probe, let's say here, this is not exactly what I expected. This white wire is 4, and it should be on 4, so it goes straight here, measuring on ground, and here is not what I expect to see. 4 and 13. So what about measuring here and here? 60 Hertz. So what about here? And this is once again 13, and they should be the same. So whatever is happening, once again I need to check wires. Probing on the mass again, and this is coming from 7, it's 30 Hertz. This is coming from 5, let's say down to 30 Hertz or something. And what is this again? Going to the red LED. Changing from 30 Hertz to whatever. So electronics show the same result. Then it is time to find out more about the hardware and about the registers. By searching around, I have found another way to set the frequencies, and I'm going to alter my code just in order to do that, and I limit myself for the pins 4 and 13. So on line 37 I comment these out, but I do add no, I do it differently. R0B, which is completely correct. However, here comes a change. I do it in kind of one and the same line. Now I have to keep in mind that I do this exactly correct, which I don't at the moment. This is correct. And now it's correct because it should be 4 and 4. And then pipe. And this is bitwise and this is bitwise OR. 1, 2, 3, 4, 1, 2, 3, 4. And this is setting 1 for 62,500 hertz. And this is how I do it, how you should do it. However, that's all nice for theory, but what I want is a low frequency. So I am going to build it up. In this case I start with 62,500 hertz, measure it on both pins 4 and 13 and see how indeed, if they indeed are the same. So this is completely binary. Let's first see if this is indeed valid code. Oops, it says it isn't valid code. (39). Ah, yes, of course. Now it is valid code. It is C, and therefore I need to put a semicolon here. So everything is alright now. Then it is time for a real measurement. And the first one I'll do off screen now. Can I do that? No, I'll do that on screen. So with the code changed, I need to change the setting of the multimeter as well, because 60 is remarkably larger than 20 kilohertz. And then first 13. Fragile connections, which I hate, but I have to deal with it for now. So how can I do that safely? Let's just put the mass here and measure safely for pin 13, and I come at about 35 kilohertz. Then keeping measuring, pin 4, which is this one, that is correct. 30, it was 32,500. Well, alright, margin in measurement, close enough. Close enough. Well, this one, this is more than 20 kilohertz too low. So I'm not buying that. Quite worrisome actually. If I take this out entirely and do a measurement on a real ground, 26. I do it here. That's odd. 30, while this ground is measuring 20, 21. That is quite odd. Would that mean that the base, that the ground is not correctly wired? You would think so. So this is mass 2, this is 28, this is 30, 30. It all should be the same. They're all measuring the same from here, because this is the measuring point with the red probe, and it should be 62 kilohertz. Alright, this is a failure. Then it is time to change the frequency to the lowest, which is 60 Hertz. And yes, that means that this probably won't go, the list that I have doesn't go as low as 60 Hertz. I can show you on camera. This is the list, and this is the lowest value, but if I go on I might receive something else, although this is 1 and this is the 1024, who knows. So on to new experiments. And that means that changing to 61 Hertz, actually 61.04, and then I need to change this setting 1024 for this. And yes, this is European writing. In American you should write a dot, I'm writing a comma for now. So this should be alright and deliver such a frequency. What I can also do is give some more lines. No, not here. So what would this give? And actually even equal curious, this quite nice to find out actually, because they have a difference from 1.864 and then 256 and 1024, and those are factors of 8. So multiplying 1024 by 8 is 8,000 8,192. But what frequency that will give, I'm not quite sure, but I will soon find out, of course. And this one, just preparing, is in a 64,000 range. If I'm correct, it's 65,000 something. But anyway, is there a limit to it? I can only find out by doing. Although this complements, of course, the 3 zeros here. So I wonder if that is the reason that they don't go further. That's not entirely true, because this leaves a 0 open, and this is not in the original list I found, but this is complementing 8 ones. So we'll find out. I have for now to comment these out, and let's upload and see. Alright, compiled and uploaded. Let's measure something. It should be 61 Hertz. So with this code change to 61.04 Hertz on both 4 and 13, let's measure. And of course I should change this to 20 Hertz, otherwise the display won't be able to display it. This is not good. This should be here. If it lets me. Yes. So this is the 4 I'm measuring, and see, it is actually measuring 60 Hertz. It can't measure lower, because of the display in kilohertz, but this is 60 Hertz. So this is good. Will this display 60 Hertz? This is most certainly not 60 Hertz. Most definitely not. So this is completely unreliable. Back to this measuring point, and this is definitely 60 Hertz. This means that 13 is not adequately configured. And that's a big disappointment. Does that mean that 13 is broken? And another question, is there a way to fix it? Because this proof is more than clear. This is 16 kilohertz or about. This one, pin 4, is clearly 60 Hertz. So there's no doubt possible. Then I can forget about 13, and let's see if I can get 60 onto other things and lower. That would be a very nice experiment, because the motors for between 40 and 120 Hertz, and if I take this sheet, this is 60, so I can try to get to 40, but regarding the steps, that will not be likely. And 120 is somewhere here. So if I can find the relationship, that would be nice. So yeah, let's go find that. Considering that this line actually gives a nice result and is actually giving the same kind of result as this line with respect to pins 4 and 13, it would be indeed quite nice to find out the differences between the 101 setting 010 and the 1024. Also the setting that actually comes first, the 100 and 250, which is factor 8. However, considering the time left for this video, there's another video of course coming up, so I am leaving that for the next one, where I can find and test a lot more. So for now, thank you for watching. Trying the registers, looking at the circuit, one step closer to a not so nice conclusion that pin 13 is not delivering its assumed output. If you like this video, please consider allowing advertisements in between the video segments. If you don't want that, please visit my website for a different way of supporting my blog. And if you haven't subscribed to my videos, to my YouTube, please do so. And this is of course most certainly to be continued with more pulse modulation on my Arduino Mega 2560. Bye bye.